Welcome to the lesson on an introduction to confidence intervals. We've said just a little bit about this in class, but we're going to be covering all that again in this lesson, and we'll be doing quite a bit more besides. Remember that if we start with a population and we know that population's mean and we know its standard deviation, then if we start taking samples of a fixed size n, this z variable here, which we obtain by taking the sample mean minus the mean of the population divided by sigma over root n, this z has a standard normal distribution. That is, that this z has a normal distribution. Its mean is 0 and its standard deviation is 1. Now we can use all that we know about the standard normal distribution to do all kinds of things, like say, for instance, we could say what's the probability that this z would be less than 1.5, or what's the probability that it will land between -2 and 2, things like that. Well, let's use our skills with standard normal distributions to take a specific example of a population, and we'll look at this standard normal variable and ask what the middle 95% of the means are that we would get by taking random samples. Okay, here's the problem we want to look at specifically. Let's say that the weights of adult male bobcats are normally distributed with an average weight of 21 pounds and a standard deviation of 2.8 pounds. We plan to take some samples of 10 bobcats, and we want to compute the average or the mean weight of every one of those samples. Now, we don't expect that every sample is going to give the same weight. So the question is this: as those sample means bounce around a little bit, where would the 95% where would the middle 95% of those averages land? Well, it turns out, and we'll argue this in just a minute, the middle 95% is going to land between the 2.5% and 97.5% markers on the standard normal distribution. Then we are going to take our formula for z. That's the one that's on just the previous screen. This z right here. And we're going to put it between those numbers, and those numbers are going to turn out to be plus and minus 1.96, and we'll reduce our inequality a little bit and we'll get this formula. Now, before I do this, I want to put your mind at rest. This looks pretty complicated the first time you see it. It turns out that it's not hard at all to work with, and the other good news is you don't have to do the algebra every time. We're always going to come up with a formula that looks like this. We're going to have the mean from the sample plus or minus some special z value. It's usually called the critical value for z, and then we'll multiply by the standard deviation of the population divided by the square root of the sample size. So we're going to be getting those numbers in just a minute, so let's jump into this calculation. Okay, the population that we're working with has an average weight of 21 pounds, a standard deviation of 2.8 pounds. And remember, we're looking at the weights of naturally occurring things, animals in this case. So those kind of measurements are very often normal. Probably these weights are pretty normal just to start with. Then when we start taking samples of size 10, the effect of the central limit theorem will kick in, and we really expect that these x-bars will be very nearly normally distributed. The mean of the x-bars is going to be exactly the same as the mean of the population, and the standard deviation actually gets better for us. The standard deviation of a single bobcat taken at a time has a standard deviation of 2.8. When we start taking the averages of 10 of those, then we expect a standard deviation of 2.8 divided by the square root of the sample size, or 10 in this case. So these things right here, x bars, are normally distributed. All right, now let's talk a little bit about how we're going to find the middle 95%. sort of, kind of, we're looking at normal distributions, going to have a shape more or less like that. We want to strike out the middle 95% of that population. And now we'll just do a little bit of thought about how much area is in these tails. Well, if 95% of the area is in the middle, then 5% has to be distributed between these two tails. Since it's the middle 95%, we're going to get 2.5% down here. We're going to get 2.5% down here. So right at this point, this is going to be at the 2.5 percentile of whatever distribution we're working with. And that point right there, that one's going to be at the 97.5 percentile. So what we're saying is the area from here all the way back is 97.5% or 0.975. The area from here all the way back is 0.025 or 2.5%. Now we can get that if we want to from our standard normal distribution. We have a handout for that. We have T distribution on the front, and the next two pages give us our standard normal distribution. So let's look down here. These are, of course, below the mean, so those are z-scores that are negative, and we're looking for 2.5%. Looks like we're getting close in this area here. Let's see, 2.5% is exactly in the table right here. Let's just get our lines together here. This is at a z-score of minus 1.9, and then we're in the sixth column. So minus 1.96 is the z-score here. And the z-score on the top end, well, we're going to have to turn the page. Those are measurements above the mean, so those are positive z's, and we are looking for 97.5% below. And look at that, it is in here exactly, once again, 0.9750. That is once again in the sixth column, so 1.96. Now, let me just tell you, this is not an accident that we got 1.96 here and we just got its negative down here. It's always going to turn out that way, because if you're thinking about the z-scores, those are centered around 0, right? So if we're looking at the middle, we're going to go the same distance here as we are here. We're just moving in opposite directions, and that's why we got these cutoffs. One is just the negative value of the other. Now, the other bit of good news is that this is such a standard and common operation that there's a little bit of a summary of that at the bottom of our table here. It says if the level of confidence is, well, we're looking for 95%, right? If the level of confidence is 95%, then the critical value for z is 1.96, which is what we have here. And that means, of course, positive 1.96 for this upper cutoff and negative 1.96 for this lower cutoff. All right, now let's say what we want to do then. We are trying to force our z values to land between 1.96 and minus 1.96. But we know something about these z's. These z's come from x minus mu over sigma over root n. And we know all those numbers except for the x. X bar, rather. The x bar, the mean that marks out the top and the bottom, that's what we're trying to find out. But the mean of the whole population, well, that is known. The mean of the whole population is 21, and its standard deviation is 2.8. So we're going to subtract off the 21, and then we're going to divide by 2.8 is the standard deviation of the whole population, and that's going to be divided by root 10. So This is the thing that goes right in here. Now, I'm not going to simplify that right now. I'm just going to write it as it is so that we'll be able to see where all those pieces end up. Because this is just going to turn into a formula that we're going to use, and we're trying to see where the pieces of that formula comes from. The formula is not magic. There's a reason for why the things are in there that are in there. So what I've got is just a numerator divided by a denominator. I'm going to multiply every single part of this inequality by this positive number here. And this is what I'm going to get, minus 1.96. That's the z critical value with a negative on it, times 2.8. That's the standard deviation of the population. Divide by root 10. That is the square root of the sample size. Then what's left in the middle is this guy, the difference between the mean of the sample and the mean of the population. And we'll have pretty much the same thing on the right hand side, except we have a positive 1.96 over here, and once again we're multiplying through by that fraction, 2.8 over root 10. Now that's good. That tells us how much we think our sample mean might differ from the population mean. But if we just run through here and add 21 to each of these three segments, then we're going to get kind of a nice formula, and it's going to be a little bit more useful to us. So this is going to tell us directly the sample means will fall between this number and this number. And we notice that this part right here is actually the same. It's just on the left side we're subtracting it, and on the right side we're adding it. So let's compute this on our calculator, and then we'll subtract and add that to 21, and we'll have our answer. Okay, the number we are looking for is 1.96. We're going to multiply that by 2.8 and divide it by the square root of 10. And that gives us about 1.7355. And if we add on this side, we're going to get 22.73, let's round that off, 6. And on the left side, we'll get 19.265. So the answer is this. We think that if we're sampling from a population with average weight 21, standard deviation of 2.8, we're taking samples of size 10. We have reason to believe that actually both of these are pretty much normally distributed. Then the middle 95% of our average weights are going to land within this range. So we think 95% of sample means fall between about 19.3 pounds and 22.7 pounds. And that's useful to know. So that is about how big we would expect average weights to be from a sample of size 10. In summary, what we did last time is we took the mean of our whole population. We used a mu rather than an x bar here. And then we added and subtracted a critical value for the z-scores and multiplied by sigma over root n, and that is actually the standard error of x bar, or you could say it's the standard deviation of the sample means. Now, we also found out that these z star, or some people call them the ZCs, the Z critical values, they're so common that we actually have a little bit of a small table at the bottom of our big table, so we can look those up directly. We don't have to work very hard to get those. Now, here's the new idea. Last time we started with mu here, which is the mean of the whole population. The question is this: what would happen if instead of using mu, the mean of the whole population, we put this x bar in here instead? Well, first of all, let's give a name to this number that we're adding and subtracting. It's this part right up here, z star times sigma over root n. I'm going to call that ME. It's actually an abbreviation for margin of error, but let's just call it ME for now. So earlier, what we did is we computed this value ME, and we added and subtracted the ME so that we could predict where the x bars will probably end up. So once we know this, the mean of the whole population plus or minus the margin of error, we can predict where 95% of the sample means will land. Now that's true because the distance between the sample mean and the population mean is rarely more than ME units. X bar and mu are usually not more than the margin of error units apart. Now, our strategy last time was this: to start with the mean of the population, add and subtract the margin of error, and that would give us a good guess of where the next few x bars will come from. Well, you could do this just in reverse. You could start with a single sample mean, x bar, add and subtract ME, and what you'd use exactly the same reason. You'd say, well, x bar and mu are not usually more than ME units apart, so x bar plus or minus this margin of error is where we would expect we could find the mean of the whole population. And now that is a very, very useful thing to do. And here's why. If we go out in real research, let's say we actually were looking at a population of bobcats in an area, we had a way of capturing them and weighing them and releasing them again. Well, we could come up with a sample mean pretty quickly. But what we probably couldn't do is get the mean of the whole population. So we could take our x bar for this one sample that we collect, we could add and subtract a margin of error, and we could say it is probably the case that the mean of the whole population lands within this particular interval. So last time we came up with 19.3 to 22.7 pounds, and what we meant was if you take another sample, it's 95% probability that that next sample is going to have a mean, an x bar, that lands between 19.3 and 22.7. Well, now we could go out and take a single sample and say, well, we think that the mean of the entire population is going to fall within a certain range, such as 19.3 to 22.7. And that would be something that's really useful to do. Because as a practical strategy, when we start doing research, we don't know the mean of the whole population. We want to figure out where it probably is. And people do this sort of thing every day in all of the sciences, in marketing, in politics, in economics, and many, many other applications. So let's summarize with a formula and get some practice in using this. All right, here's our next one. Suppose that the mean of our sample is 19.5, the standard deviation is 4.2, the sample size is size 10. We would like to get a 95% confidence interval for the mean of the whole population, and it's done using this formula right here. So let's do the calculation. The mean of our sample is 19.5, the standard deviation of the population is 14.2, and we have 10 different observations that feed into that sample mean. We would like to estimate the mean of the entire population. And this is a much more realistic situation because normally in research we might know the mean of a sample, but we generally don't know the mean of the whole population. So we want a 95% confidence interval. We should be specific here and say for mu, that's the mean of the entire population. Well, our formula is this: x bar plus or minus z star or zc or z crit, however you like to write that, the z critical value, and then we're going to multiply by sigma over root n, where sigma is the standard deviation of the whole population and n is the size of the sample. All right, from the beginning, if we didn't already remember it, we could look up in our table right here, confidence interval critical values. We're looking at 95%, so 1.96, and the next digit, they're not indicating it here, but it really is a 0, 1.960. So we know that. The standard deviation of the population is 4.2. The size of the sample is 10, and the mean of the sample was 19.5. So let's get this value. This part right here, let's just review. This part right here is called the margin of error. A lot of people will refer to that as ME, just abbreviation for margin of error. And this right here, of course, this is the sample mean. And some people call that the point estimate. What they mean is, if you got to give just one number rather than a whole range for your guess for mu, well, it would be x bar. So 19.5 is a point estimate, but 19.5 plus or minus the margin of error would be the range in which we think you could probably find the mean of the population. Okay, our calculations next. We want 1.96, that's our critical value for z, multiplied by 4.2, the standard deviation of the population, and divide that by the square root of 10, which is the 10 is the sample size. So we're getting about 2.603. And that is being added and subtracted to x bar, 19.5 minus previous answer, and that number is 16.90 if you round off to 2 decimals. And for our upper value, we'll take 19.5 and we'll add this 2.603, and that's going to give us 22.10. So what we're saying is we are 95% confident that mu, that's the mean of the whole population, lies between 16.9 and 22.10. So what we're doing is we're starting with information about a sample. That's this right here. And we're saying we're now giving some quantifiable information about the whole population. We really have turned a corner here. If you think about it, in the past, we've always done this. We've said, suppose we've got a population And we would say something about its mean, something about its standard deviation, or maybe something about the proportion of things that have a trait of interest. And then we'd say, okay, now we're going to take out a sample, and we want to predict something about x bar. We want to predict something about the standard error of this x bar back here in the sample. Well, now we're doing just the opposite. We're starting with information about the sample, and we're going back and giving information about the population. When you're going in this direction, you're doing what is called descriptive statistics. So we are simply describing what's happening in this population, and we can say something about what would probably happen in a sample. When you're going in this direction, this is what people usually mean when they talk about inferential statistics. Get partial information about this population and then infer something about the entire population. And we've gotten started with that quite nicely. Other thing I want to mention is that we actually have a formula here, and that is sitting right here. That is the formula for a confidence interval, and it's a specific one. There's lots of different confidence intervals you could compute. This is the confidence interval for mu, the mean of the whole population, and furthermore, it's the one you use when sigma, the standard deviation of the whole population, is known. One last thing I might mention here, and that is someone could argue this way, and by the way, they'd be 100% right. They'd say, well, you got started by this by saying it's much more reasonable to assume the sample mean rather than the population mean, and then infer something about the population mean from the sample mean. That is reasonable, but what about this? You've assumed that you know the standard deviation of the whole population. Well, good grief, if you didn't know the mean of the population, why would you know the standard deviation? That is absolutely 100% a fair criticism. And what we're going to do in the next class period is we're actually going to remove that assumption, and we'll do pretty much what you would expect. Here we started with middle 95% of sample means. We started by putting a mu here, and we replaced that population mean with a sample mean. And now in the next step we will be replacing this population standard deviation with the sample standard deviation. The catch is you don't use the z critical numbers anymore if you do that. There's some other critical numbers, and we'll learn about those later. But that is to say, if somebody's been wondering, that seems a little unrealistic, why would we know that? You're 100% right. It is unrealistic in most situations, but we can work with it anyway. We'll get another formula that's very similar to this one, and honestly, it really won't be any harder to do the calculations for those. Okay, we have been kind of plotting, and we need to pick up the pace here, which we will. We're going to be able to knock out the rest of this quite quickly. We've started with a sample mean and a population standard deviation and asked for a 95% confidence interval for mu. That mu is the mean of the population, not of the sample. We used this formula to do it, and originally that was a 95% confidence interval. Let's redo this, and we'll pick up the pace here and show how to do it efficiently. And we're going to do it for 90 and 99% confidence intervals as well now. Okay, we've been here. Here's the mean of our sample, standard deviation of the population, sample size 10, the formula we used for a confidence interval, and last time we got this range. That is for 95% confidence, 16.9 to 22.10. We want to redo this now. We've done it for 95% confidence. Let's do it for a confidence level that's lower and higher, so a 90 and a 99, and we'll compare to these and kind of see how that plays out. Okay, here's our setup. We want to redo what we did before with 90% confidence. The big difference then is going to be this Z critical value is going to change. The 95% Z critical value, 95% was 1.96. 90% is a little smaller, 1.645. Everything else in the calculation is the same. Sample mean is 19.5, sigma 4.2, and sample size is 10. So let's compute that. Once again, that's the margin of error. That is the point estimate. So we're going to be adding and subtracting something to the point estimate. So we want 1.645 multiplied by standard deviation, divide by square root of the sample size. And we get 2.185. All right, there's a 90% confidence interval. The 95% confidence interval we already did, but let's just copy that down so that we have it for reference here to 22.10, and then the 99% confidence interval. Well, we're going to do the same thing all over again. It's always x bar plus or minus the Z critical value times sigma over root n. X bar, the mean of the sample was 19.5. We call that a point estimate. The critical value we'll get from our table. We're now interested in 99% confidence. 99% confidence, 2.58 is the critical value. Then we multiply by the standard deviation of 4.2, divide by the square root of the sample size, and as before, we'll compute our margin of error. 2.58 times 4.2 divide by square root of 10. And that gives me a margin of error of 3.4. Let's round that off to 3. 3.43. Add and subtract to 19.5 to 22.93 for 99% confidence interval. Let's just line these up, shall we? 90% confidence. That gives us 17, and we'll try to make this simple so we can see what's going on. 17.3 to 21.7. 95% confidence. So now we have higher confidence. We're more sure that mu will be in this range. 16.9 to 22.10. And if we want to be really sure, we're 99% confident that mu will land in the range. Then our range is going to be 16.1 if we round off to 22.9. Now let's just take a look at what's happening on a number line. In all of these cases, these are all 19.5 plus or minus something. So 19.5 is in the middle. That's our point estimate. At 90% confidence, we come out here a ways to 21.7 and back a ways, same distance actually, to 17.3. Then, if we want to bump that up to 95% confidence, so we're more confident, this goes up to 22.1. That's out a little further, right? 22.1 and down to 16.9. That's back a little further. And then finally, if we wanted to push this even further in terms of confidence and be 99% confident, then we'd go even further out here. 22.9 and down here back even further to 16.1. Now, notice what's happening. We're saying we're 99% confident that we're going to be in this widest range here. We're 95% confident that we're going to be in this narrower range here, and we're only 90% confident that we're going to be in this range right here. That kind of makes sense, doesn't it? If we want to be more confident, then we give ourselves a little bit more room for error. And then, of course, this distance out here from the center out to one end of our interval, whether from here to here or from here to here, that's called a margin of error. And the name should start to make a little bit of sense. We say, well, I'm going to give myself a margin of error of, back in this case, about 3.43 units. So I'm going to take my best guess and I'm going to add and subtract 3.43 units. That's adding and subtracting quite a bit. We're taking an overall range of double that. Of that 3.43, we go that both to the right and to the left. So of 3.4, we're getting about 6.8 for the length of our whole interval. We give ourselves a range of values that's 6.8 units long. Well, we're pretty confident. We're 99% confident that we trap the true value of mu. If we add and subtract something much smaller, about 2.2 instead of about 3.4, well, then that puts us down here in this range. And we say, you know, we're less confident. Now we're only 90% confident we'd fit in this smaller range. That is generally the way things work. As the confidence level, the width of the interval also goes up. And the opposite is likewise true. As the confidence level goes down, the width of the interval also goes down. Now, the width of the interval is directly related to what we call precision. Precision is how repeatable a measurement is, or how close you are to being able to stay at the same level again and again. And so what we're saying is that if you don't want a lot of confidence, then you could have really high precision, which is to say you'd have a really narrow interval. On the other hand, if you want a lot of confidence that you've trapped the true value in your range, well, then you'd probably want a bigger interval, right? So confidence level and the width of the interval always do the same things. They both go up or they both go down. Okay, we need to say just one more thing about these confidence intervals, and that is to give a caution about using the language of probability as we describe them. Earlier we said that we had a 95% confidence interval for a mean that ranged from 16.9 to 22.1. And what we mean by that is we think that the true value of the mean of the population falls between those limits. Now, what I didn't say is that there's a 95% probability that the mean of the population falls within those calculated limits. And here's why. The true mean is a fixed number. It's already there. And it's either in the confidence interval or it's not in the confidence interval. We don't know which one it is, but it's either there or it's not there. So technically, in terms of probability, it's either 100% probability that the mean is in the confidence interval or a 0% probability that the mean is in the confidence interval, but frankly, we don't know which one it is. What the language of confidence does is it shifts the probability not from whether the mean is in the confidence level, but rather it shifts that probability to the method or the formula that we are using. So the method or the formula is what the probability is attaching to. 95% confidence means this, that that confidence interval is computed by a formula or by a method that works 95% of the time. In a particular time, it either worked or it didn't. But when we say that we have a 95% confidence interval, we mean the method we used will capture, that is, between the low and the high value for the interval, mu is going to be in there, 95% of the confidence intervals you construct using this formula. In the same way, a 90% confidence interval means that if you produce lots of confidence intervals with this formula, 90% of the time the mean of the population is going to be in there, and 10% of the time it won't be in there. And you could say the same for a 99% confidence interval. So that's the caution you want to use when you're thinking about probabilities and confidence intervals. For a confidence interval, it's already computed and the mean is already fixed. So the mean is in there or it's not. The probability attaches to the method, or you could say to the formula. The formula captures that mean 95% of the time, or 90% of the time, or 99% of the time, and the rest of the time it fails. For any particular interval that you compute, though, we don't know. The mean might be in there, it might not, but we have a sense of confidence that it's there, and we can quantify that as 90, 95, or 99% typically.